conjugate pairs theorem. Complex zeros always occur in conjugate pairs. If a plus bi is a zero, then a minus bi is also a zero. Those are called conjugates. When you have the sign in the middle is positive on one of them and negative on the other one. We use conjugates sometimes when we're trying to get stuff to cancel when we're multiplying it together because it turns into a difference of squares. And so it gets rid of our middle term. So you'll never have imaginary zeros occur in odd numbers. You'll never have 4 imaginary zero or 3 imaginary zeros. They will always be in pairs. You'll have 2 or 4 or 6 or 8. They'll always be in conjugate pairs. Okay, so the real factorization theorem says fx can be factored into a product of linear factors and irreducible quadratic factors. So like we just saw on the previous page, remember how I said, we don't really usually leave factors with imaginary numbers. We usually multiply those out and call them irreducible quadratic factors instead. So this is kind of like good math manners, bad math manners. It's not really wrong. It's just that we kind of like everything we do to be in the real number system. And so by multiplying that together, we get this. Do you want to test it out? Do you want to see if it's true if you multiply together? Should we just do that really fast? I don't know. See if I can think about it. X times x is x squared. X times 2i is 2xi, I guess. And then negative 2i times x would be negative 2xi. And then negative 2i times positive 2i would be negative 4i squared. But I squared is the same thing as negative 1. And negative 4 times negative 1 is positive 4. So that gives us the positive 4. We have the x squared right there. And the 2xi and the negative 2xi cancel out because that's what conjugates do. And that gives us our irreducible quadratic factor with all real numbers in it, even though its zeros are imaginary. Okay, we're going to do example 3. And as we do example 3, I'm going to kind of slow down and talk about something you should have learned in 2.4 if you watched those videos. So I'm actually going to erase this and start fresh to talk through the rational roots theorem. So the rational roots theorem allows us to take infinitely many possibilities for zeros into a finite few number of possible zeros. It's just a theorem that works to reduce the possibilities. It doesn't give us the actual zeros. We have to check those with synthetic division. It just gives us possible numbers. Okay? So the coefficient of our leading term is 1, and our constant term is 12. We're going to call factors of 12, we're going to call P. And factors of our leading coefficient, we're going to call Q. And we're going to figure out all possible factors of those. So our rational roots theorem, these are like our possible rational zeros or potential. Either way, both are kind of the same thing. Possible, I started writing possible and then potential and turned it into a combination of possible rational zeros theorem. I cannot spell today. Okay, so P over Q. And P is the factors of 12. All possible factors of 12 over all possible factors of 1. So what are all possible factors of 12? Anything, whole numbers we can multiply together to get 12. Yeah. So 1 times 12, 2 times 6, and 3 times 4. So you see why we include 1? Okay, so then what are all the possible factors of 1? Okay, so we don't even really need that one. So our possible rational zeros, or potential rational zeros, are 1, 2, 3, 4, 6, and 12. One thing I forgot to mention is that factors of 12 aren't just these numbers. It's not just 1 times 12 and 2 times 6 and 3 times 4. What about negative 1 times negative 12, or negative 2 times negative 6, or negative 3 times negative 4? So you always have to consider the positive and negative possibilities as well. So that means we don't just have 1, 2, 3, 4, 5, 6 possibilities. We actually have 12 possibilities because we have the negative and positive possibilities for each one. Okay, so that takes infinitely many possibilities down to 12. Now we use synthetic division to figure out what ones actually work. I usually start with the ones because they're fast and easy to do, and if they don't work, oh well. Then we move forward to the harder ones. But if the harder ones don't work, then we do all that work with the harder ones just to find out that the easy ones were the answers to begin with. So, yes, question? Good? Okay, so what is the easiest number to start with? Perfect, let's try it. So we're going to put our 1 in a box that came from that list, and I'm going to take my coefficients from my function 1, negative 3, 3, negative 5. Thank you. 0 and 12. Don't forget to pay attention to the exponents. We have a 5th power, 4th power, 3rd power, 2nd power. There's no 1st power. And then a constant. We have to put that 0 in for the missing term, or it messes up the places for our division. Okay. Bring down the 1. 1 times 1 is 1. Negative 3 plus 1 is negative 2. Negative 2 times 1 is negative 2. 3 plus negative 2 is 1. 1 times 1 is 1. Negative 5 plus 1 is negative 4. Negative 4 times 1 is negative 4. 0 plus negative 4 is negative 4. Negative 4 times 1 is negative 4. And 8. Not a factor, because there's a remainder. So is 1 a 0? No, it's not a 0. We tried 1 of our 12. So 11 to go, possibly, unless we find them all. All right, we're going to keep going. We might run out of space. I don't remember how much space I gave you. Did I give you much space? I gave you the rest of the page, so that's good. Anyway. All right, before I erased it, does anyone remember what one of the answers was? So we can just go to numbers. Save us some time. Negative 1? Yeah. That's usually the one I try next time. So usually just to not confuse myself, I'll go ahead and cross off anything that doesn't work so that I know to ignore it. I don't erase it off my paper. It was part of my work. I just didn't work. Okay, it's 1, negative 3, 3, negative 5, 0, 12, 1, 1, negative 2, positive 2, positive 5. Am I doing this straight? Uh-oh. Nope. I read 1 times negative 1 is negative 1. Negative 3, negative 1 is negative 4. 4 and negative 1 is positive 4, which is 7. 7 and negative 1 is negative 7. Somehow I'm amazed at how this always works out. Negative 5 plus negative 7 is negative 12. Negative 12 times negative 1 is positive 12. Plus 0 is 12. Times negative 1 is negative 12. Plus 12 is 0. Whew. 5 possibly on their mind. I got one to work. So what do I know about that 0? I'm going to start making a little list of zeros over here just to kind of keep them out of the way as I go. So negative 1 is a 0. Now what if negative 1 has a multiplicity? Is it possible I could divide negative 1 into my answer and get it to work again?
Yes.
It is possible. Should we try it? Because I know it's not going to work. So I don't know if we want to add that to our math. We could. It's fine. So I'm just going to go to this step really fast. Come on. I can do it. My math skills are off today. 5, 12, negative 12, negative 24, 24, 36. -1. It only worked once. Sorry, so that part didn't work. So now I'm going to go to this part again. So I'm going to focus back on this answer. I'm not going to go to my original anymore because I already divided that out. So I tried 1 and -1. What would be the next easiest one to look at? 2, probably. Let's do like multiplication with 12. It's not that easy. Kind of is. Not too bad. Could be a good way to practice your 12 times tables. I don't trust myself on it today though. I'm making all sorts of mistakes. So I'm going to try 2 because -1 didn't work a second time, but I'm not using the original problem. I'm using the answer from the one that did work. All right, bring down 1. 1 times 2 is 2. -4 plus 2 is -2. -2 times 2, -4. 7 minus 4 is 3. 3 times 2 is 6. -12 and 6 is -6. -6 and 2 is -12. Jackpot. We got 0. So 2. Now, is it possible that 2 could have multiplicity? We better try it again then. So let's try it again. So, bring down the 1. 1 times 2 is 2. 0 times 2 is 0. 3 times 2 is 6. Oh, it worked. So what does that tell us about our 0, 2? Multiplicity of 2. How many zeros do we have so far? Technically 2, but with multiplicities we have 3. What's the degree of our polynomial? 5. We need 2 more. So here's what we have left at this point. The 0 is the remainder. So that means that this number will be our constant. I just kind of go backwards. This one would just be x, and this one will be x squared. You go that direction and knowing that's your remainder, you know, and then you go up from there. Okay. So that gives us the equation x squared plus 3. That is an irreducible quadratic factor. It can't be factored. Irreducible quadratic factor. So at this point, we could write our problem in factored form. I think I neglected to actually read the instructions. Find all zeros and state their multiplicities, factor f to linear and irreducible quadratic factors. See, that statement right there is how you know to not leave your factors as imaginary. You leave them real. Okay. So we still need to find the rest of our zeros. So what we're going to do that, even though this is an irreducible quadratic factor, we're going to set it equal to 0, move our 3 to the other side, square root both sides, which gives us plus or minus square root of 3, which is -3, sorry, which is also known as plus or minus I square root of 3. You can't take 3 out of the square root without it being like an approximate answer, rounded decimal answer. So there's our other 2 zeros. So we have positive I square root of 3, and we have negative I square root of 3. There's all of our zeros right there. Now we just need to write our polynomial in factored form using those zeros. So f of x equals x minus a -1. So what happens if you subtract the -1? X plus 1. The multiplicity or the power would be 1. So we don't need to write it. So then we have x minus 2, multiplicity 2. So what's our power? Squared. Yeah. And then we have our irreducible quadratic factor, which was x squared plus 3. We have now written our polynomial in factored form. We know the zeros, which means we know the x-intercepts. We know all the factors. There are a lot of different things we can do with that in this form. We can graph it with knowing the x-intercepts, the end behavior, all that, right? All right, let me stop the video. I'm sure it's really long.